Hey, Science and today we're going to be discussing topic 2.2 of the electricity unit, modeling and measuring electricity. Thus far, we've discussed three measurements of electricity. I introduced you to amperes, which otherwise known as amps, which measures the current of an electrical circuit, the amount of electrons that are moving through a circuit at any given time. I've discussed with you voltage, measured in volts, which is the electrical potential or the energy potential of a circuit. And I've also mentioned ohms, which is the unit of measurement for resistance, which discusses how much a part of a circuit is going to sort of restrict the flow of electrons. Now, it's sort of hard to kind of visualize what all of these means in an electrical circuit. So what I like to do, and what a lot of teachers like to do, is they like to describe these three units or these three measurements in terms of something that people can visualize, like a waterfall. So what I've got here is I've got three waterfalls drawn here, and these represent the three waterfalls that are in your notes down here, and they're labeled the same. I've got waterfall A, waterfall B, and waterfall C over here. You'll notice that two of the waterfalls are higher, one is shorter, and A is much wider than C, and C is much wider than B. So what does that all mean? Well, first of all, A has the widest river entering the waterfall, or the widest waterfall. So what does that mean? What does waterfall A have more of? Does it have more voltage? Does it have more resistance? Or does it have more current? And if you want to just quickly try to make your predictions right over here, I'll let you know which one it has. Well, waterfall A has got more current. It's got a much larger flow of water. It's not as high, but it certainly has a lot of water exiting over the waterfall. So waterfall A would represent I guess, a large current. So if you could imagine current being like water, electrical current being like current in a river, the more water that is flowing over the waterfall at any given time, that's going to represent the current. Well, what does what's the difference between then A and then B and C? B and C are the same height. They have a much further distance for the water to flow. To fall down. They have a much larger potential for the water to fall a greater distance because they are higher. So what would the waterfall then be? The height would determine its what? Would it determine its voltage, or would that would that be analogous to the resistance of the waterfall? Take a look and maybe give me a quick answer up here before I give it away. And what the height of the waterfall would be analogous to in an electrical circuit is, in fact, the voltage. Think about it like potential energy. If I hold like a marker this high as opposed to this high, this marker has less potential energy than this marker because I've raised it up higher. It has a much larger potential to fall a greater distance and to gain kinetic energy. In this case, these waterfalls have the higher potential, the same idea for kinetic energy, but in the terms of an electrical circuit, the higher the voltage, the more potential there is for the energy to flow through the circuit. Okay, so that's what the height of the waterfall would sort of imply. The potential energy that would be in an electrical circuit. Now, the last thing we have to discuss is resistance, and resistance is anything that impedes the flow of electrons. Well, that is pretty easy if you think about it. Which of these waterfalls has the greatest resistance? Well, it's the one that has the smallest flow, regardless of height. If this waterfall here was very thin, even though it's a shorter height, it would still have lots of resistance. So in theory, what we're dealing with resistance is anything that's impeding the water flow over the waterfall, or in the case of an electrical circuit, it's impeding the flow of electrons. So in this case, just to kind of recap, the wide waterfall would be analogous to an electrical circuit that has lots of current. Waterfall C and B would be analogous to circuits that have lots of voltage in them, lots of the potential for energy in them. And C would indicate the waterfall that has the most amount of resistance, whereas A would be the one that has the least amount of resistance. Now, you may have noticed something there, that current and resistance are sort of opposite. The more I have for current, generally the less resistance there is. If I have less current, which I do in the case of B, I tend to have more resistance. And we'll get to that here in just a couple of seconds when we discuss Ohm's law. One other analogy that you can think about when you're thinking about electricity in a circuit, and it's up on the slide right here if you've got your notes up in front of you, is using a pipe. If you use a pipe analogy to discuss electricity, pipes that have smaller diameters, smaller openings in them, and have a longer distance to go, like longer distances to travel, tend to have more resistance because the pipe is smaller or it travels over a longer distance. There is more possibilities for the pipe to have impediments that are going to block the flow of water. So a long and narrow pipe is going to be a pipe that has more resistance, whereas ones with larger diameters and shorter distances to travel are going to be the ones that have the least amount of resistance. And again, the other thing about so how this applies with an electrical wire, pardon me, is that if you've got a circuit that is longer, a longer circuit, a longer wire, even though it's a conductive wire, the longer a wire is, the more resistance that could actually happen in the circuit. Now, I alluded to this in the 2.1 video when we talked about superconductors. I talked about that in the last lesson, and how if we have superconductors, there would be little or no loss of electrical transmission. I think I used the analogy of having a power plant in Edmonton delivering power to Jasper. If you had a superconductor, you would not lose a lot of the electrical energy, and that's what we're getting at. The longer the transmission lines are from where the electricity is starting, or where the energy source is, to where we're going to actually power a load, that distance is going to increase the amount of resistance. So this is one of the reasons why in the last video I talked about the importance of the research behind superconductors, because this would prevent distance being an issue in circuits if we were using superconductors as opposed to just the regular conductors that we are using right now. Okay, let's get back to a scientist who I introduced you to in the last video, Georg Ohm, who was a famous German physicist who did a lot of work on Volta's voltaic pile, the first battery ever invented in 1799. He did a lot of experimentation early on in the years of electrochemical science or electrochemistry. And he discovered something very quickly, well, not maybe quickly, but through his research, he discovered that there was actually a relationship between these three measurements of electricity. He discovered there was a relationship between voltage and resistance and current. And that relationship got put into what is called now Ohm's law. He kind of proposed this law, and we still follow this law today because it's just as accurate now as it was back when he proposed it in the early 1800s. And that law states the following. He said that the resistance of a conductor will remain constant if you keep that conductor at the same temperature. Now, we talked about how superconductors are more conductive when you drop the temperature. So you can't take a conductor and make it hotter or colder, because the hotter the conductor is, the more resistance that would be in the conductor, and the cooler the conductor would be, the least, or I guess less resistance would be in that conductive material. So this is predicated on the fact that the resistance will remain constant as long as the temperature doesn't change. But he said with that, he also discovered at the same time that the amount of current will be directly proportional to the amount of voltage. So basically what he said is, if your resistance remains constant, what you're going to find is that current and voltage will both increase together. They will be proportional to one another. And as I mentioned in the diagram up here, I said that resistance would be indirectly proportional to the amount of current. So in other words, if I have more resistance, I'm going to have lower current. And if I have higher current, I would have lower resistance. So that's also part of this law that isn't in the notes, but there is an indirect or an inverse proportional relationship between current and resistance. Whereas voltage and current go up together. If my current goes up, my resistance goes down, and if my resistance goes up, my current goes down. So there's an inverse relationship between current and resistance. So well, how does this all play into it? Well, there is an equation that plays into Ohm's law. First of all, do you have to memorize the equation? No, you don't. On an exam, on a quiz, on a unit exam, on a pad exam, this formula will be given to you. But they're only going to give you one formula. And the formula I believe they give you is voltage equals IR. So voltage is equal to the, and voltage, by the way, is measured in V. I is the measurement of current, and R is the symbol used to show resistance. So I is current, R is resistance, and V is voltage. So in this case, voltage is equal to the current times the resistance. Now you can reword or you can rework this equation into two other equations. You can also, it's the same equation, just you're just moving your variables around. You could also say that current is equal to voltage divided by resistance, or you could say resistance is voltage divided by current. Now, a lot of people have trouble rearranging equations. So I'm going to show you a little trick. And actually a grade 9 student taught me. A grade 9 in my Science 9 class taught me this trick, so thank you to that anonymous student who I won't mention here today. You draw a little triangle like that, right? And if you've got an equation like V equals IR, you basically write IR like you're multiplying them together. So IR gets put in the bottom, which means that the only thing that goes on the top now is V. So what this triangle represents is this. If I want to know what V is equal to, V would be equal to I beside R, which would imply multiplication. So V equals IR. Hey, there we go. V equals IR. Beautiful. Well, what if I want to calculate my current? My current would be V over R. V over R. Well, I equals V over R. Look at that. That works really well too. And the final one is, what if I want to calculate my resistance? Well, according to this, resistance is going to be voltage divided by current. Resistance is equal to voltage divided by current. It works out really well. So if you know one aspect of the equation, you can plug it into the triangle, and then you can figure out all the different variations of the equation. So just to keep that in mind, it's kind of a cool little trick that a grade 9 student taught me a couple of years back, and it's I thought it was brilliant. I never was taught that, so that was a great method. Maybe you guys know about it, and I'm just too old to remember such things, but there you go. Before we move on with the application of Ohm's law, take a look at this video right up here about a review on electrical current and how we measure electrical current and the relationship between current, voltage, and resistance. All right, so that'll be a good video to watch. Crash course video, fantastic one to kind of recap not just what we discussed here today, but over the last few lessons, what we've discussed about current and voltage and resistance. Alrighty, so that's all fine and dandy. So Ohm told us that there are basically three, the three measurements of electricity are all connected together mathematically. But how do we in real time measure voltage? How do we in real time measure current? How do we in real time measure resistance in a circuit? Well, what we have for that are what we call test meters. Test meters are used by electricians to measure various aspects in a circuit. So, for example, and they're all actually they're pretty obviously named. Their names basically tell you what they measure. The first one are voltmeters. Okay, well, a voltmeter is going to measure what? A voltage. It says voltmeter. It's got to be voltage that it's measuring. But what voltmeters do is, so imagine this is a battery. This is my positive end. That's my negative end. If I had a voltmeter, I would actually stick the voltmeter like these would be my fingers. These would be the two ends of the voltmeter, and I would measure the potential difference in the battery. So this was a AA cell. Remember, they're AA cells, not AA batteries. The AA cell, if I were to measure this, this usually has 1.5 volts. Well, if that battery is fully charged and I basically put my two ends of my voltmeter on either end of that battery, I should measure roughly 1.5 volts in a full battery. The lower that voltage is, the closer it gets to zero, that means that the battery is being depleted. So when you measure voltage in a circuit, you have to measure it between two parts of the circuit. You just can't stick a prod into a circuit in one spot and say, what's the voltage? because the voltage is based on a difference. There has to be a difference, there has to be a drop in voltage in the circuit to indicate what the drop in potential energy or electrical energy is. That is known as the voltage drop, and I'll get to that a little bit more specifically as I show you a great little diagram coming up here on the last board for today's lesson. Voltmeters can measure in volts, capital V, or they can measure in millivolts, which is little m, capital V. Remember, it's just like all other units we've talked about. There's like kilograms, milligrams, grams. A millivolt is 1/1000th of a volt. There would be 1,000 millivolts in a volt. So it's the same. Remember, millipede means 1,000 legs. So when you do this, if there's any kind of millivolt calculations, remember you can't mix your units. Remember your units, if you have volts in the equation, you can't use milliamps or milliohms. You have to use them all in milli to make it consistent, right? So most of the questions you're going to get are going to be in volts. I don't think you're going to get a lot of questions in millivolts, but just be aware. We've had this conversation earlier in Science 9 already. The second test meter that we use are called ammeters. They're not called amp meters. They're just called ammeters. That isn't a typo. They measure the current in a circuit. And you don't have to use two prods for an ammeter. You just basically put the ammeter right on the circuit and you measure the amount of electrons that are flowing through the electrical circuit at any given point. So that's what an ammeter does. If it measures small currents, like ones that maybe have milliamps, that has a special name. Those ammeters are referred to as galvanometers. They measure very small electrical currents and very small electrical circuits. The third test meter, it's not in your notes. I just wanted to kind of throw it at you just because it makes sense that why wouldn't there be a third meter for the third unit of measurement? You're not officially needing to know this, but I just wanted to throw it in anyways. Ohm meters are going to measure resistance, and they're going to measure the resistance of an object in the circuit, how much resistance that object has, whether it's a load or a resistor or a rheostat, any of these things that will cause resistance in a circuit. And it's going to measure them in ohms, which is in that little omega, the Greek omega symbol that you can find hidden away on your keyboard if you hold the option key down. And then as well, it can also measure small amounts of resistance in milliohms, which would be little m, and then the omega symbol beside it. There are some test meters out there that can do all three. You can switch between being a voltmeter, an ammeter, or an ohm meter, and those are referred to as multimeters. So there are multimeters as well that will measure potential, well, all three of them, and you just have to switch between what setting you're going to use to measure any particular aspect of an electrical circuit. Okay, so how do you put these meters into an electrical circuit? So here we've got an electrical circuit that looks a little bit more in depth than what you've seen in past diagrams. Let's quickly dissect it. I've got my battery on the top. I can tell it's a battery because it's got two tall lines and two short lines. If it was just a cell, it would be tall and one short line only, as I discussed in our last video. The tall line is representing the cathode. The small line is representing the anode. You'll notice there are three loads on the circuit. There are three light bulbs, 1, 2, and 3. You'll also notice that I've got V1, V2, V3, V4 in circles. Those V's with circles represent voltmeters. And you'll see that the voltmeters are not directly on the circuit. They have to be in front and they have to be on both sides of an object on the circuit. I need to see what the potential difference is in the voltage before it enters a load and when it comes out of the load. And every time I see a drop through, because the load is going to convert some of that voltage into another form of energy. So you're going to get voltage drops as you move through either anything that's going to give you resistance in the circuit. You're going to see a voltage drop. And that's where these voltmeters come in. If I just put a voltmeter like in the middle of the line, like my ammeter over here, it would measure nothing because there's no difference. It's measuring voltage at only one part of the circuit. A voltmeter has to measure two parts of a circuit in order for it to work. You can't measure the voltage on a circuit at only one point. You have to have 2 points of measurement to measure the drop, whether it's on either side of a battery, which is my voltmeter number 4, or whether I'm measuring the voltage drop on this first light bulb, second light bulb, or third light bulb. Okay, so those are my voltmeters. The last meter that I've already alluded to is my ammeter, which is the circle with an A in the middle of it. That's the symbol. in a schematic diagram for an ammeter. And the ammeter just has to sit on the circuit to measure how many electrons are flowing through the circuit. It can measure amperes at one spot. It doesn't require 2 points of measurement because it'd be like you sticking a device in a river to see how fast the water is flowing. You don't have to stick that thing at two different parts of the river. You know what the current is at that particular part of the river based on the flow of the water. You don't have to have 2 points of measurement to measure current in a circuit. So that's basically, so this is a schematical diagram of not just the circuit. This is my actual circuit right here. These little lines here just represent connection points onto the circuit. Now, can electricity flow through these? Yeah, sure it can. And you'll be able to tell that, at this point the voltage is something, and at this point the voltage is different, and it's going to actually indicate to the voltmeter what that difference is. And I'll get to that here on the last slide when we sort of connect everything that we've discussed. Well, this is my last slide, but I'm going to add some stuff to it actually before we finish up today. So let's do an example. We know, first of all, that my formula is V equals IR. So we're gonna do a little scenario here, and you can follow along in the notes. The slides there below me. Try not to look at the answers. See if you can calculate these on your own. You might want a calculator with you at this point, just to give it a shot and see if you can kind of follow along at home. Try to look at the slide over here because all the information I'm just going to be reading off the slide. So what we're gonna do is we're gonna set up a circuit here, and we're gonna use a 9-volt battery. So my power source is going to be 9 volts, and I'm going to have a current that's flowing through my circuit of 2 amps. So 2 amps is going to be my circuit. That's going to be measured at that point by my ammeter saying, yep, we got 2 amps of current running through. So I've got my volt reading, I got my voltage reading, and I've got my current reading of 2 amperes, okay? So what I like to do now is I like to, and I also know this as well, pardon me. I also know the resistance of the three loads that are on my diagram. So light bulb 1, light bulb 2, and light bulb 3. The resistance of light bulb 1 is going to be 3 ohms. The resistance of light bulb 2 is going to be 1 ohm, and the resistance of light bulb number 2 is going to be 1 ohm, and the third light bulb, is going to be 0.5 ohms. So I've got 3 light bulbs, one with a 3 ohm resistance, second one has a 1 ohm resistance, and the third one has a half a ohm resistance. So those are the resistances of the 3 loads on the circuit. Okay, so now you've got that sketched out. So the question, we're going to ask the first question here. What would be the voltage drop on the first light bulb? Okay, so what I'm needing to calculate here is what is the volt drop. Now remember, the initial voltage on my battery is 9 volts. That isn't the drop. There's going to be a drop in that voltage that's going to occur when it hits this light bulb. What I want to know is what's the drop off of the 9. So I'm going to have 9 volts coming in, but at the end I'm going to have another voltage at the other side because part of that voltage has been converted into another form of energy. It's been converted into light, into heat in the light bulb. So I need to know what the volt drop is. So when I calculate voltage, I'm going to do the first one for you just so you can kind of see what I'm doing here. So in this case, I need to use these values here. I need to know what the resistance of that load is, or that resistor, and I need to know what my current is, and I know both of them. I know that I've got 2 amps of current entering the light bulb that has a resistance of 3 ohms. So I'm going to plug that into my equation. So V equals IR. My I is going to be 2 amperes, and my resistance is going to be 3 ohms. Well, 2 times 3 equals what? I'm going to have a voltage drop of 6 volts. And again, if you look at the notes, I'm kind of flicking them up here one at a time here. On yours are going to be all showing at once, but you can see that is now it's a 6 volt drop. So let's try the next one. So the second question is, what's the voltage drop across the second light bulb? Well, in this case, my resistance is now 1 ohm. My current, according to Ohm's law, does not change. We talked about that as part of Ohm's law. The current is unaffected by any resistors in there. You're going to see the change in the voltage. So there is an overall change, but it's going to be expressed through the voltage. The current of electrons, they still have to go somewhere. They're going somewhere. The electrons aren't sort of disappearing. So what we're dealing with here is we've got now a voltage drop. Let's get rid of that 3. We're going to plug in now a 1. So we got 2 amps of current, going through the 1 ohm resistor. That's going to give me a volt drop of 2 volts. And that is, in fact, my volt drop over the second light bulb. Now let's go to the third light bulb. The third light bulb, well, it's only got half an ohm of resistance. You guessed it. We're going to plug half an ohm into that equation now. And that's going to drop this down to 1 volt. So we're going to get a voltage drop across light bulb 1 of 6 volts. We're going to get a voltage drop across light bulb 2 of 2 volts, and the third light bulb, we're going to see a drop of 1 volt. Now, I've got an interesting question for you, and if you've looked at the notes already, you kind of maybe already know the answer, but if I add up those 3 voltages, those 3 voltage drops, what do I get? Well, I have a voltage drop of 6, a voltage drop of 2, a voltage drop of 1. 6 plus 2 plus 1, what the heck does that equal? That equals 9 volts. Why is that significant? My battery is 9 volts. All the voltage is used to the 3 different loads that are on the circuit. And that's actually a law in electricity. It's actually known as Kirchhoff's law, which I think you'll learn about more in physics. We do cover, I know, in Science 30, but it's kind of an interesting thing that all the voltage essentially gets swallowed up by the current before the electrons sort of return back to home to the battery. So that's how you calculate your various your various voltages and currents and resistance. Now, again, just a reminder: use your triangle. This little triangle here is going to come in really handy when you're doing your questions today. There's going to be all sorts of questions where they're going to get you to calculate voltage based on current and resistance, or you might have to calculate the current based on the resistance and the voltage. They're going to kind of play around with the variables a little bit on your homework for today. And that homework is as follows, right here on the bottom of the board or right over here. You got skilled practice questions 1 to 3 on page 307. As well, you're going to have questions 1 to 10 on page 310 of your textbook, and that's going to be due as part of this assignment for this video. Thanks a lot for tuning in, everybody, and we'll see you again next time for electricity topic 2.3.